Hi, I thought I'd just do a quick video on the power monitor circuit since it's something that I'm going to be working on again soon, but it requires quite a bit more design work. I've decided that because of some challenges that I faced in the existing design, I think I want to sort of take another look at it and start over. Um, so one of the things that I've been looking at today is the front end circuitry for the actual current sensing. And we've got an equivalent circuit of what I've come up with today here. So this part on the left here, we can think of as the actual current sense, the actual current sensor. So the clip-on SCT split current transformer that clips onto the line that's being measured. And the way that this has been implemented in this particular simulation. Is just a voltage source, an AC voltage source, going into a voltage-controlled current source in such a way that this generates a 50 milliamp peak, 50 milliamp peak signal when fed with a 100 amp signal. That's basically how the particular split current transformers, the SCTs that I'm using, work. So when you've got a 100 amps being fed through this AC line, it generates 50 milliamps at its output. And we can then turn that into a voltage by putting it across a burden resistor. Now, in this case, we've got a 10 ohm burden resistor, which is the maximum that's allowed according to the data sheet of the SCTs. And what using Ohm's law, we know that V equals I times R. So we've got this current 50 milliamps, and we've got 10 ohms. So 50 times 10 is 500. So what happens is we get this 500 millivolt drop across the resistor, which generates a 500 millivolt peak signal. So that's 500 millivolts positive to 500 millivolts negative. So the peak to peak voltage is 1 volt. Now, most designs that I've looked at that utilize this design either make a mistake, which is to use a much larger burden resistance, which is not allowed according to the data sheet, in order to generate a larger voltage, which can cause all sorts of problems and non-linearity, and generally is not a good idea. Or they just stick with the 10 ohm resistor and take that 500 millivolt, that 1 volt peak to peak signal, and feed it into an ADC. Now, if your ADC has an input range of, let's say, 5 volts, you're only using 1/5 of that range for that signal, which is not ideal. Preferably, you want to use as much of that range as possible. You know, and even on 3.3 volts, you're only using 1/3. And also keep in mind that you're only using that 1/3 or 1/5 when you are sensing a full 100 amps through that circuit, and 100 amps is a lot of current. Generally speaking, most of the circuits that you're going to be measuring are probably not pulling 100 amps. They're probably pulling 1, 2, 3, maybe 20 amps, maybe 30 amps at most, but they're probably unlikely to be pulling anywhere near 100, which means you're wasting a lot of your sort of measurement range on your ADC. And because ADCs have a finite resolution, so they might be, let's say, 12 bits or 10 bits, that means that each individual bit has a sort of, if you take the total number of possible measurements that it can take, so on a 10-bit ADC, that's 1,024 steps that it has. You take your range and you divide it by the number of steps, and you get the what's known as the LSB value. So it's the amount of current that you're measuring per least significant bit in that ADC. So the less range you use, the more that sort of chunk of current will be per least significant bit, and therefore the less resolution you actually get out of it. And that could mean that you can only actually tell the difference between, let's say, 50 milliamps at a time or more, which at 230 volts in the UK is when you multiply that out, is a few watts. So it's not that accurate, not that high resolution. So what's a nicer way to do things is to amplify that signal up and use more of that ADC's input range. So if we take a look at this circuit, that's effectively what we're doing. Now, we can ignore this part at the top. In fact, we can ignore all of this. What effectively we've got is this 2.5 volt bias voltage. This is the reference voltage. And this sort of injects 2.5 volts into here, the DC into here, which means that the generated voltage signal in this top line here that I'm highlighting ends up being 2.5 volts plus whatever the voltage drop over the burden resistor ends up being. So let's say it's as high as, plus minus 500 millivolts. That means that this signal, in terms of voltage, can be as low as 2.5 volts minus 500 millivolts, which is 2 volts, or as high as 2.5 volts plus 500 millivolts, which is 3 volts. So you get this waveform that goes between 2 volts and 3 volts. Now, this is also fed into the other terminal of the op-amp. And the reason for doing this is that if you feed this DC bias voltage into the signal that you're measuring here and also into the other terminal, it effectively cancels out inside of the op-amp so that when the gain is applied, it's only applied to the signal and not the DC bias. So you're not multiplying the DC bias up, you're only multiplying up the signal that you're applying on top of that DC bias. And the end result of that is that you can DC bias your output while also applying a gain without causing any problems. Now, since we know that the ADCs are going to be measured at up to, well, from 0 to 5 volts, 2.5 volts is a good midpoint reference for that. And ideally then, now you might think, oh, well, that means that we would like to have a signal of up to 2.5 volts either way, so plus 2.5 volts or minus 2.5 volts. Now, while that would take advantage of the complete range, that does start to run into problems with when you're approaching the rails of the op-amp. So op-amps can't, while you can get rail-to-rail ones, and I am going to be using a rail-to-rail one, they don't exhibit the best behavior when you approach the rails very closely. So if it's fed by 5 volts, if you go very close to 5 volts or down very close to 0 volts, they don't behave the best. So ideally, what you want to do is have a bit of a buffer space between this positive rail up here, and ground. So you don't want your signal reaching all the way up to the positive rail and all the way down to the negative rail. So the idea here is that we take this 1 volt peak to peak signal and we multiply it by 4 to create a 4 volt peak to peak signal. And because that's offset by this 2.5 volts, what you effectively get is going 2 volts either way of that, you get 4.5 volts at the highest peak, and you get 0.5 volts at the lowest peak, which gives you a nice little margin away from the rails there. Even though I am using a rail-to-rail op-amp, it's still ideal to give yourself a bit of room. And this gain is set by this resistor and these resistors. And we're going to ignore these for a moment. So here we've got what adds up to a 5k ohm resistor, and we've got a 15k ohm here. So when you add 15 to 5, you get 20, and then you do 20 divided by 5, which gives you 4, which tells you the gain. Now, this is great. It means that you take this input voltage, this input current signal, which then gets turned into this voltage signal here, which then gets amplified up, and you get a much larger range on the output. Great. But since we don't generally always want to be measuring a full 100 amps on every circuit, I mean, 100 amps on every circuit is a lot. You know, if I had 100 amps flowing through every circuit in this house, I would be doing the "this is fine" meme because everything would be burning down. Generally speaking, most of the circuits, in fact, all but possibly 1 or 2 of the circuits that I'm going to be measuring are limited to 32 amps by the breaker. And they're designed to not go above 32 amps. So 32 amps is just 1/3 of that total signal. So ideally, we would want to be thinking about using that full range for for the 32 amp use case, instead of just 1/3 of the range. So what we can do is we can have a gain select, so that when we know that we're only going to be measuring a 32 amp circuit. Now, I've had this set to 32. If I change it back to 100, we can see here that the, or at least you will in a moment when it goes past my camera, you can see that the waveform is, forming these quite large peaks. Here we go. We can see this here now. So the peaks here go as high as 4.45 volts. So that's, for a 100 amp situation. So you've got 100 amps flowing through the circuit, and this is what you would see. Now, if I change that back to the 32 amps that we would see, the waveform goes back to looking like this. This is a much smaller range. And for most of the circuits, that's all we'd ever need to see. So what if we could change how much gain we've got? Well, one way to do that is basically just add some additional resistance here, and by default, short it out, and then open the circuit when we want to just measure 32 amps. So this then turns this total resistance up here. It adds an additional 40k to the 15k. And then when you add all of it up, so you've got 5 plus 15 is 20. That brings it up to another 20, so that's 60. 60 over 5. Effectively, you get a gain of 12. Or 3 times the original gain, which is good. So obviously it was 4, and now it's 12, so that's 3 times as much. So for a 32 amp input, we can now see that it's generating these same peaks again. It's back to this 4.45 volts. It's generating this high peaks and using the full ADC range, which is ideal. Now, having just a jumper here, like a physical jumper that you have to plug in and out of the board, that's okay. But the software also needs to know about it. Now, you could have the user just, select the right, the right gain value so that they get the right values out of the board. But that's not ideal. What would be much nicer is if the board knew automatically which gain had been selected. And what would be even nicer is if the board could select the gain itself. Now, obviously, a board can't just, pull a jumper out, a physical jumper out, because, the MCU can't. It doesn't have hands. So you might think, okay, well, what if we used a relay? That's okay. It's got some ideal properties in terms of the actual switch, but the driving them requires a higher voltage usually. I mean, yeah, you can remove 5 volts, but they pull quite a bit of current. It's just not ideal, and having that, you get mechanical bouncing issues and all sorts, and they're quite large. They take up space on a board. And you could look at something like an opto transistor, but in this particular case, because it's an analog sort of situation, you don't really want to use something like that. So what you can use instead is an analog switch, and there are ICs that do this. Let's have a look at one. So this is one of the analog switch ICs that I've been looking at. And you can see the diagram here. It's quite simple. You've effectively got this switch with 2 inputs and 1 output. So it's a single pole double throw switch that can take any analog signal, flow through here in both directions. And this enable pin, which effectively just swaps which signal is switched on, which input is being used. And, it can be powered from 1.8 volts to 5.5 volts. It does have some on resistance, so it's 2.7 ohms. But when you consider that we're talking about, 40k or 15k or 5k, I mean, on the high end of it, it's 15k and 40k. 2.7 ohms is nothing. It's within the tolerances of the resistors themselves, to be honest. So that's fine. But these switches do have an interesting property. Now, if we take a look here, so these are the DC characteristics. It just says DC here, but it doesn't make a difference for the 5 volt supply. And we can see here that there's some leakage current. And what this is effectively current that can flow across the switch while it's in an open state. So even though you've got it switched to, let's say, A1, how much current can flow through from A2 to B? It can leak through. Now, typically this is 0.01 microamps. That's tiny. That's, 10 nanoamps. Who cares? It's so negligible, we don't need to think about it. But maximum is 1 microamp. Now, that's potentially more of a concern. And if we go back and look at the circuit, we can start to see why. So if we look here, imagine that when this switch is switched off, there's 1 microamp still flowing through here. Now, if we use Ohm's law, we can think about that in terms of resistance, because we've got a voltage and a current. So when you plug the numbers in, if we've got 2.5 volts flowing through here, you effectively get the equivalent of a 2.5 mega ohm resistor across these two resistors. And when you work that out, now in my original design, these resistor values were twice as high. So this was 40k each, so you had 80k here. And when I worked it out, that actually generated an error, a resistance error of about 3.25%. And that's quite high. And not only is it quite high, it's also non-linear, because this is not a resistance, it is a leakage current. So as the voltage changes across here, the effective change in resistance over here also changes, which is a little bit nasty because it creates this like non-linearity. As the voltage goes up and down, the effective resistance here also goes up and down, so you get this non-linear response in gain, and that's not ideal. So I halved all of these resistor values. Now that does it does us a nice favor of halving the amount of error, and it's actually ever so slightly better than half for slightly obscure reasons. But the negative side of doing this is that there's more current pulled from the voltage reference because these resistors are a lower value. Now, luckily, the voltage reference that I decided to use was already 50 times more. Had a 50 times higher current rating than I actually needed, so it's a massively over-designed. These parts are cheap; they're jelly bean parts. You can just buy them for next to nothing. So picking one with a decent amount of current capability, this 5 milliamps, was enough. And consider that there's going to be 16 of these channels. Even then, it was 50 times over. So by halving these resistor values, it just gives us 25 times over, which is still way over, way over spec. It's absolutely fine. So this can supply 25 times more current than we actually need, which is fine. But what it would be nice to do is to be able to simulate the leakage current. So that's what these Xenodiodes up here do. And what I've really done, and I apologize that you can't really see the numbers here, but what I've done is I've made these Xenodiodes and I've put them back to back. And I've given them a breakdown voltage of 100 volts, which in this circuit means that they'll never break down because they're way, way, way lower voltage. We're only passing 4, at absolute peak could only be 5 volts because we've only got 5 volt supplies. And I've set the forward voltage to just be 1 millivolts. This tiny forward voltage, so it's effectively, we don't even care about that. But the saturation current is set to 1 microamp, which is the same as the leakage current. So what happens is when a voltage is applied over here, you do get this leakage current, and this simulates the same effect. So when I turn this on, you get this leakage current passing through. And what happens is that the waveform on the output actually changes due to this leakage current. So normally you get a peak voltage of about 4.406 volts. Now if I just hit reset on this, I can see that it comes only up to 4.366 volts. So this Xenodiode, this leakage current generated by this sort of model here, the Xenodiodes aren't really here. This is just modeling the leakage current of the analog switch IC. And we can see that this is a 4.366 volts instead of the original voltage, which was 4.406. And I'm looking over at my screen on the left here because I've got the calculations over here. And if we then go and take a look at what that is in percent, that brings us down to around 1.8% error, which is acceptable. Now, we could lower these resistances even further, but that starts to get a bit, we're really starting to tax this voltage reference. Then, okay, yeah, it would be 12 times as much as 12 times the amount of current it can supply, 12 times the amount of current than we actually need, which is still, it's tons. But since we only have one supply here, the more current you start pulling through here, the more noise you start to get, the more sort of noise you generate because of all of the different signals being fed in at the same time. It starts to be more of a problem. The more overhead you have here, basically the lower impedance that this whole pathway is, because you've got this, this high drive current, the less noise you get. So you start to get diminishing returns as you reduce these values, and you use more power. The circuit uses more power in total. So I'm still sort of looking into alternative options for having this switching. I may well not do automatic switching at all. I may just have it as a manual selector. But I thought this was quite a neat little exploration of leakage current and a way to simulate that leakage current. Now, the only other things in this circuit are a low-pass filter here, which is, I think, tuned to about, I don't know, I think it was about 800 hertz or a kilohertz or 1.2 kilohertz, something like that. And that's just to remove any additional noise that might be coming through here, and a Xeno diode to clamp the output to some reasonable amount. So there's not really much more going in here. But this is a nice sort of representation of the circuit design that I'm looking to build, and also some of the capabilities that we might be able to gain out of it. And I still haven't decided whether I want to get that additional bit of precision, or have the sort of convenience of the feature of being able to turn these on and off. I'm sort of tending towards not being able to automatically configure them, because having the physical jumpers and just changing them once when you install the device, it's not it's not something that you need to change all the time. You would just set it up once, and that should be fine. So I think that's probably okay, but it is also kind of cool to be able to automatically select it. So I haven't quite decided. Maybe I'll come up with something where I find an analog switch that has a much lower leakage current or something like that, and I'll still be able to do this. But either way, I thought it was quite a nice little exploration of modeling leakage current and looking at all of the parameters of the circuit and seeing what happens when all of these properties are introduced. So I will hopefully be streaming soon on this design and working on it again. My other project, the RGBW over RS485 stuff, which I nicknamed Horus 485, those boards have now been manufactured and will be with me soon. They should be getting posted, so I'm very excited for that. So I expect more streams working on some of the sort of physical assembly of all of that, or at least videos of the results. I don't know whether I'll stream any of the actual hardware putting together, because it's kind of a little bit difficult to film. But yeah, so definitely some videos on building this again soon, and we should hopefully have a nice 16-channel home power monitor before too long. So thanks for watching, and I hope it was informative.